Let's take a look at some other definitions. If P and Q are statements, then we can define P only if Q. It means that if not Q, then not P. Or equivalently, we can write it this way: if P, then Q. So be mindful of different terminologies that we are using, different orders, different wordings that you're using to represent implication. John will break the world's record for the mile run only if he runs the mile in under 4 minutes. So what's the meaning of that? We can write down different version of it. For example, we can write, if John doesn't run the mile in under 4 minutes, then he will not break the world's record. Or you can write it this way. If John breaks the world's record, then he will run the mile in under 4 minutes. So if P, then Q, meaning if not Q, then not P, or P only if Q. As you remember, we say P then Q is equivalent to its contrapositive, which is not Q, then not P. And another way to represent this is P only if Q. This is your P only if Q. Let's move on to another definition. Given a statement variables like P and Q, we can define something that we call biconditional of P and Q, which is P if and only if Q. This is called biconditional of P and Q, usually represented by double arrows. P if and only if Q. It is true if both P and Q have the same truth values. So it doesn't matter if both of them are true or both of them are false. We can use a truth table to write them in compact form. If P is true and Q is true, by definition, P if and only if Q is also true. If P is true, Q is false, then you get a false back. Let me use the same color as pink here. And if P is false, Q is true. Since they have different truth values, you get false back. And if both of them are false, since they have the exact same truth value, P if and only if Q is going to be true. Okay, let's see what's next. The order of operations for logical operators. Well, the very first operation that takes priority is negation. First, we evaluate the negation. Then we move on to and or. We evaluate and or, and if there are basically no parentheses or grouping symbols involved, we need to ask the author to give us some information about the parentheses or grouping symbols as well. And finally, we have implication and if and only if. We want to show that P if and only if Q is equivalent to P then Q and Q then P. So wherever you see P, if and only if Q, in a theorem, in a lemma, you can basically use its logical equivalent to rewrite it. On the left-hand side, we have P if and only if Q. On the right-hand side, you have a combination of two implications. Since we have two statements, 2 to the power 2 is 4, you get 4 combinations or 4 rows. P, Q, P if and only if Q, you have P then Q, you have Q then P, and you have P then Q, and Q then P. So we want to show that two columns are the same. P can be true, it can be false, but since we have two statements, the combination is going to be 4. Q can be true and false as well. So true, false, true, false. By definition, true if and only if true is true. True if and only if false is false. False if and only if true is false. And then false if and only if false is true. This is by definition, correct? So let us keep them in mind that we have this for definition of biconditional statement. Now let us take a look at P then Q. P is true, Q is true, P then Q is true. P is true, Q is false. This is the only case that the implication is false. Q is false and Q is true, so you get true back. P is false, Q is false, it is true as well. Now Q then P. Okay, be careful about the order. Here you have true, then true, which is true. False, then true, which is true. True, then false, it gives you false. And false, then false, which is true again. Now we are combining these two together, right? We're combining these two using and. Well, true and true is true. False and true is false. True and false is false. True and true is true. Now our goal is to compare these two columns, right? The very first true value is true, the second false, the third is false, and the last one is true. So we just showed that P if and only if Q is the same as P then Q and Q then P. Now remember that the order is not important. So again, wherever you see P if and only if Q, you can substitute that using P then Q and Q then P. Let's take a look at more examples for you. In this definition, you have two statements like R and S. R is a sufficient condition for S. It means that if R, then S. So that's the definition of sufficient condition. R is sufficient condition for S. It means that if R, then S. R is a necessary condition for S. It means that if not R, then not S. So we define sufficient condition and necessary condition. R is a necessary condition for S also means if S, then R. So if S, then R. Remember that this is equivalent to not R, then not S. So if not R, then not S. This is basically the contrapositive of S, then R. R is a necessary and sufficient condition for S, it means that R, if and only if S. So again, try to feel comfortable about these terminologies. Later on, when we're trying to prove a lemma or theorem, we're going to go back and forth using sufficient condition and necessary condition. So again, sufficient condition is the same as implication. R is sufficient condition for S. It means that R then S. But when we say R is necessary condition for S, it means that you have S then R.